In this video, we take a look at what it means for a function to be increasing and decreasing, and then figure out how we can use that information to determine more about the function and maybe how it has some relative maxes and minimum values with the first derivative test. So the first thing I want to do is kind of draw a picture here and show you what it looks like when a function is increasing and decreasing. And this is really kind of information that you already know. It's just applying what we've learned so far in calculus to the shapes of graphs and what that derivative then gives us. Okay? So say I've got some function f of x that looks like this. It's kind of like a weird looking u or a v. And I've got two interesting values here. We'll call them a and b. If I look at this picture here, I can see that to the left side of a there, my function has like negative slopes. If I pick an x over there, and I do it in red, or like this pink color, to denote that this is a decreasing value, right? If I were to calculate the slope at x there, I would get a negative number. And I can see as x moves to the right, that trend continues, right? As x moves to the right here, that trend continues. Okay, so what I would say is that my function in that interval, in that little space to the left of a, I would say that my function is decreasing. Okay, and that's because we have negative slopes, right? As I move to the right, the function is getting smaller, right? It has smaller values. In between a and b here, if I choose an x, we can see that the slope in there just looks to be 0. Right? That would be like what we would call a constant slope. And as I move x to the right, that trend continues, right? So as I go to the right for x, what does my function do? It stays the same. It's constant in that interval, okay? And then finally here on the right side of b, if I pick an x, that x, when I calculate the slope of my curve at that point, we see a positive slope, a green slope. And as I move x to the right, my function gets larger, right? I go up, and therefore I've got a positive slope or an increasing function. Right? And we're going to relate all of this back to what we know about the derivative now. We know the derivative gives us the slope of the tangent line. So in each of these intervals, we can describe, based on what we know from the picture, that our function is increasing, constant, or decreasing, what the slope is. Here we have positive slopes when my function is increasing, 0 slopes when my function is constant, and negative slopes when my function is decreasing. That's going to tell us everything. In fact, we know pretty well how to calculate the slope of the curve at a point, right? We take the derivative and we plug in a point. So what we'll do is we'll take a derivative, plug in the point, and we'll see if that slope is positive, negative, or 0. And then we can describe what our function is doing, whether it's decreasing, constant, or increasing in that interval. Okay? So what we say here is that f prime is negative. The derivative is negative to the left side of a. The derivative is 0 in between a and b, and the derivative is positive, greater than 0, for x's that are to the right of b. Okay? And I just want to lay these out in kind of a listed format here without the picture and more mathematical notation. What we would say, and this is theorem 4.5 in the book if you're looking, if my derivative is positive for all x in an interval from a to b, then we can say that the function f, not its derivative, but the function f is increasing on that closed interval from a to b. Okay? Very similar, if f prime of x is negative for all x in a to b in that interval, then f is decreasing on that interval. Okay, so the information that I'm extracting about the function is coming from the information I'm getting from the derivative, if that makes sense. I'm looking at the sign, sign, of the derivative to determine what the function is doing. And lastly, if f prime of x is 0 for all x in an interval, then the function is constant in that interval. So what I want to do in the rest of this video is kind of explore a few examples here and be able to lay out a process for describing when a function is increasing, decreasing, or constant, and then use that information to hopefully extract something about extreme values. Okay. So let's look at an example here. I want to find the increasing and decreasing intervals for this function x cubed minus 3 halves x squared. Okay, and if you want to go backwards, you can. But we use the derivative to find all of our information. So I'm going to take a derivative here. I get 3x squared minus 3x. Easy derivative of a polynomial there. And what I really want to look for here is when that derivative is positive or negative, okay? And to do that, I'm going to first figure out when it's neither. I kind of got some cases, right? I've got whether the derivative is constant or when the derivative is 0, when it's positive or negative. And I'm just going to try to tick those off. The first one, the easiest one, is to figure out when it's 0. In fact, what we'll be looking for here really are critical points. We're going to look for critical numbers of our function. So that's when the derivative is 0 or undefined. In this case, we don't have any values for where our derivative is undefined. So what we just set our derivative equal to 0 and we solve. I've got 3x times x minus 1. And each of those set equal to 0 gives me values of 0, x equals 0, and x equals 1. So I've got two critical numbers here, 0 and 1, and those are kind of going to create the shape of my function. Basically, I'm going to work around those values. Think of those as like the a and the b in our previous slide here. So I'm going to put these guys on a number line, 0 and 1, and then I'm going to construct the intervals that I'll be testing in. So basically, these critical numbers are going to break apart my real number line, right? This polynomial has a domain of all real numbers, okay? And those critical numbers are basically going to be places where I might see a switch from increasing to decreasing or decreasing to increasing or constant slopes along the way. So those are kind of my starting point. I put my critical numbers on my number line. A lot of times you'll see people use a table for this. It's all the same information. I just prefer the number line instead, so that's what I use. So what I do is I then need some test values. I need numbers inside each of these intervals to plug in to my derivative to check the sign, S-I-G-N. Remember, for all of this, I'm looking for when the derivative is positive, negative, or 0. I know when it's 0 already, right? I'm not going to find any more of those. I know when it's 0, so I'm just looking for if there are places where there's this derivative is positive or negative, and they're going to occur around these critical numbers. So I need what we call test points. And for us, I will pick numbers that are easy to plug in each of these intervals. So say -1, 1/2, and 2. That's the best I can come up with. Just nice, as round as you can get numbers, right, to plug in to your, not to your function, but into your derivative. Okay? So I'm going to take my derivative. In fact, I'm going to take it in factored form, right, that 3x times x minus 1, and I'm going to plug in each of these test points. Again, I made up those test points. You could have chosen -6, 1/3, and 17. All right. As long as they're in those three intervals, at least in this specific example, then you're fine. So I plug each of these test points into my derivative. Okay. So I take -1 and I plug it in for every x in my derivative. I've got 3 times -1 times -1 minus 1. All right. And what we get from that, and what I get from that is a -3 times a -2, or a 6, which is positive. I, in fact, don't even care what the number is. I'm just looking for the sign. So that's a positive number. I'm going to put a plus sign here in this interval from -infinity to 0. So what I've got is my derivative is positive in that interval. And what that indicates, a positive derivative means my function is increasing. So I'm going to put those arrows in just a moment. I'm going to evaluate my derivative at all of these other test points here. So I need f prime of 1/2. Plug in a half, I get 3 times a half times 1/2 minus 1. When all said and done, -3/4, that's negative. I don't care what the number is. I just know that it's negative, which means my derivative is negative there. Same thing on the third interval here. I've got 6 again, just by happenstance. 6 is positive, so my derivative is positive. Okay? Now, on each one of these intervals, I can use that information from the derivative to gather more information about the original function. So all of that is information about the derivative. Okay, the derivative is positive, negative, positive. Cool. That's what those plus, minus, plus means. From that, I can say that my function is increasing, decreasing, and then increasing on each one of those intervals. Okay, I'm going to write this out a little better, but this is basically how I go about the process. All right, I find my critical numbers, I put those on a number line, and I test points around those critical numbers in my derivative. I gather whether the derivative is positive, negative, and then I use that information to describe my function, whether it's increasing or decreasing. Easy peasy. So here's that function and its derivative again. Again, the first step is to find those critical numbers where the derivative is 0 or undefined, right? I didn't have any of those in that last example. In fact, I don't really have any in the rest of the video, but we always look for undefined values for our derivative. We look for critical numbers. A lot of times you'll be looking for vertical asymptotes, okay? I can't plug in vertical asymptotes, right? I'm going to have to test around those, okay? So just try to keep that in mind. I test values in the intervals surrounding those critical numbers, okay? So that's where those that negative 1, 1/2, and 2 came from, as I plugged in around those critical numbers, okay? And I plug those into the derivative, right? I'm looking for when the derivative is positive or negative to tell me what is going on with the function. So in the previous page, we saw that the derivative evaluated at -1 was positive, which means that f is increasing on the interval where that test value lives, right? So that test value lives in the interval from -infinity to 0. So the function is increasing on that entire interval. Why isn't there any other, why is that whole interval taken care of? Well, I found where the derivative was 0. There's not any other chance for the derivative to be 0 on that interval. And there's no vertical asymptotes or any parts of the function that are discontinuous or anything else I have to worry about, okay? Usually we take that all into consideration at the beginning, okay? F prime of 1/2 was negative, so that implies that my function is decreasing on the interval where 1/2 lives between 0 and 1. And finally, f prime of 2 is bigger than 0, so we say that f is increasing on the interval from 1 to infinity. So I've got all the information from my derivative there as it pertains to my function. I know where the function is increasing, decreasing, and I can combine those, right? So I can basically say, I can combine these two lines to say that my function is increasing on -infinity to 0, and then again from 1 to infinity. Okay. I want to show you what this function looks like. In fact, that little sign chart that we used on the previous slide here is enough information basically to come up with a rough sketch of the picture of this function. We just need some more information. So here's that graph. Here's what the function looks like. I've plotted it in Desmos here, and I've already taken the two critical numbers and I've put those on my graph. So I've got 0, 0, and 1, -1. Okay. If I want those values, actually what they are on my function, I would plug 0 and 1 into the function itself, not to the derivative, but into the function. Okay? And I'm basically just going to create the sign chart around this picture. So I've got two critical values, and I'm going to denote kind of splitting up my real number line with blue lines here. Think of those as the A and B, right? Those two critical numbers. Those are like my sign chart, the two values on my sign chart. And then I've got intervals 0 to 1 where my function is decreasing. And we can see that in the picture, right? I see that the slope is negative there. My function is decreasing. Right? That's it. It's decreasing on the interval. I found that by plugging in 1/2 and extracting that the derivative was negative there. I can do the same thing on either side. From minus infinity to 0, my function is increasing, and I can see that with the picture, of course, but we were able to extract that with just the derivative. And finally, on the right side here, from 1 to infinity, I see positive slopes. I can say that my function is increasing. Now, one of the cool things is that you'll notice where these critical numbers are also potential locations of maximum and minimum values, right? Those are little like hills and valleys. And I can extract that information using the changing of signs here with my derivative. So I'm going to put this on a number line again. I know that my derivative is negative and positive on those intervals there. And I denote then with the arrows what my function is doing. So I go from increasing to decreasing to increasing, right? So the sign chart on the left should match the graph on the right. Everything is happy. And what I can say is that my curve actually has a shape here like this, going from increasing to decreasing around 0. So we would say that around 0, my function goes from increasing to decreasing. My derivative goes from positive to negative. And I know it's constant at 0, right? The derivative was 0. That is an indicator that I have a relative maximum at that point. I can say that since f is going from the derivative is going from positive to negative, or because the function is going from increasing to decreasing, I've got what we call a relative max. And very similar, going from the interval from 0 to 1 to 1 to infinity, my derivative goes from negative to positive. My curve goes from decreasing to increasing. I see this kind of shape around a constant slope at 1. That's an indicator that when x is 1, my function has a relative minimum, because the derivative changes from negative to positive, the function changes from decreasing to increasing, I've got a relative min. This is the starting point. This is basically the basis for what we call the first derivative test. The first derivative test. And all it is just using a changing of signs in our derivative, or a change in increasing to decreasing, or vice versa, to extract whether we have a relative max or min. Okay, I'm going to lay out that definition here. The first derivative test. There's a lot of words here. I'm gonna sprint through it and basically kind of get to the punchline. You can copy all this down if you like. Let C be a critical number of f that is continuous on an open interval containing C. If f is differentiable on the interval, except possibly at C, right? Remember that C can be, if C is a critical number, then the derivative can be undefined there. We can use information then to classify f of C, not f prime of C, but f of C. What is the function doing at C? We've got some different cases here. The first is that if f prime of x changes from positive to negative, and of course that means that my function goes from increasing to decreasing at C, then f of C is a relative maximum, right? Follow the arrows. My function is going from increasing to decreasing. There's a maximum somewhere there in between. And in fact, that maximum is going to occur at my critical number. Just the opposite, if f prime changes from negative to positive, and again in black there, I'm showing the arrows of my function, not the derivative, but the function. My function is going from decreasing to increasing, then f of C is a relative minimum. Follow the arrows. And lastly, there's of course a case where we have really no information. F prime of x does not change sign around a critical number. It's possible. Doesn't seem like it, but it absolutely is. I can have a function that doesn't change sign around a critical number, in which case I have neither a max or min. Think of f of x equals x cubed. X cubed. I've got a critical number, x cubed, when x is 0. There's a constant slope when x is 0. Or there's a 0 slope, when x is 0. And on either side, of that critical number, my function's increasing. So there are definitely examples where that occurs. So that third bullet there is required. I just want to do one more example where I'm actually applying then this first derivative test. And it will really feel like finding intervals where our function is increasing or decreasing. It'll feel a lot like that first example I did. So the process is basically the same. I'm going to take my function, look for critical numbers. I'm going to test points around those critical numbers. And I'm going to determine if the derivative is positive or negative, and therefore determine if the function is increasing and decreasing. And then I'm going to determine whether I have a sign switch, whether my derivative changes from positive to negative or negative to positive. And then if that indicates a max or a min. So find the relative extrema is basically how we summarize that. Of f of x is 1/2 x minus sine of x on the interval from 0 to 2 pi. Okay, so I've got to give an interval here. Otherwise, I would be finding an infinite number of critical values because of the way that sine oscillates. So of course here, first thing, derivative. Here's my function. My derivative should be 1/2 minus derivative of sine is cosine. So I want to know where this derivative is equal to 0 or where cosine of x is 1/2, right? If I add cosine of x to the other side, I've got cosine of x is 1/2 on the interval from 0 to 2 pi. Okay, well, cosine of x is 1/2 at every angle like pi over 3. So if I look at my little cheat sheet here, ASTC is my quadrants of my unit circle. All students take calculus, ASTC. In the first and fourth quadrant, I've got cosine is positive. Okay, so I'm looking for a pi over 3 angle in the first quadrant and fourth quadrant. So that'll be pi over 3, and then in the fourth quadrant, 5 pi over 3. Okay, so those are two x values that are critical for my function, and there would be more, right? But I've got my interval from 0 to pi over 2, or I'm sorry, from 0 to 2 pi. I only have one revolution on my unit circle. All right, so those are my two critical values. I'm going to test those. So here's my number line. I'm gonna box it off with my interval from 0 to 2 pi. I've got pi over 3 and 5 pi over 3 somewhere along the way. And I need test values. Okay, so from 0 to pi over 3, I've got a test value. I can use like pi over 4. From 0 or from pi over 3 to 5 pi over 3, I can use pi over 2. And then 7 pi over 4 between 5 pi over 3 and 2 pi. So if it helps you to draw out some of your unit circle there to get those test values, that's totally fine. Just looking for values in each of those intervals. And you'll see that my number line isn't exactly perfectly to scale, right? Because if I draw my unit circle here, I've got this sort of shape, and pi over 3 is here, and 5 pi over 3 is here. Okay, so I'm looking for test values in this interval, in here, anywhere in here, right? And then 5 pi over 3 is all the way over here. I need one more test value. So my intervals aren't exactly equal, right, of equal length. I just put them on a number line to space things out nicely, okay? And again, all I'm looking for is when the derivative is positive or negative. I'm looking for a sign when I plug each of these test values into my derivative. So first, I check pi over 4. I do f prime of pi over 4. That's 1/2 minus, and I'm plugging these into my derivative here. So what is cosine of pi over 4? That's radical 2 over 2. 1/2 minus radical 2 over 2. Well, 1 is smaller than radical 2, so when I take 1 minus radical 2, I've got a negative value. Negative value indicates that my derivative is negative, which means my function is decreasing. So I do it all right there in real time. Next, from pi over 3 to 5 pi over 3, I'm testing pi over 2 as my test value. plug in pi over 2. 1/2 minus cosine of pi over 2 is 0. So 1/2 minus 0, that's positive number. So my derivative is positive. My function is increasing. Okay. Lastly, plug in 7 pi over 4 into my derivative. And I've got, again, 7 pi over 4 is in the fourth quadrant. Cosine of a pi over 4 angle in the fourth quadrant is positive. So I get another radical 2 over 2, which means I've got a negative derivative. Negative slope means my function is decreasing. So each of these I can then tell my function has a relative min, because my function goes from decreasing to increasing around pi over 3. That should be a relative min. And a relative max, as my function goes from increasing to decreasing around 5 pi over 3. Okay? So for this function here, 1/2 x minus sine x, I can say that because of the signs of the derivative of that function, where the slopes are negative and positive and where they change sign, I can extract where my function has a relative max or min. And we can do this with any function. Any function. So the process is basically this, right? I'm looking for intervals where my function is increasing or decreasing, where my derivative changes sign, or where my function changes from decreasing to increasing, or vice versa. Around critical numbers, pay attention to vertical asymptotes when you're doing these types of examples and working through the homework, because those are going to come into play. However, I can't actually have maxes or mins at vertical asymptotes, right? So even if my function were to change from increasing to decreasing around a vertical asymptote, I can't have a maximum at a vertical asymptote, though I can change sign around one, right? Just think about it as a breaking up of your interval, of your domain, okay? All right, that's it for this video. Thanks for watching.